Welcome to a special presentation of the American Rock Mechanics Association. Today, we're proud to host Dr. Taha Husain, who is the co-chair of our Underground Storage and Utilization Technical Community, presenting a special seminar on geomechanical support for drilling operations, overview of the basics and available technologies, to the ARMA student chapter at the University of North Dakota.
That is a good opportunity for the ARMA student chapter to start our first webinar here today, and you, Dr. Bameh, as well. He says that he's gonna be after he's finishing his.
Hello everyone. So ARMA student chapter at UND is honored today to have Dr. Taha Husain presenting today. This webinar is a fruit of collaboration between ARMA UND and Underground Storage and Utilization Technical Community. So Dr. Taha is a geomechanicist with expertise in reservoir geomechanics for highly depleted or water flooded reservoirs. And also he has a master's in reservoir engineering and a PhD in geomechanics from Penn State University. His PhD involved numerical modeling of which required thermomechanical coupling during lava dome eruption and magma emplacement using discrete element modeling. And Dr. Taha, now he is working for Shell Exploration and Production Company for the last 6 years as a development petrophysicist. His presentation is entitled Geomechanical Support for Drilling Operations, overview of the basics and variable technologies.
Thanks, Abdul. Feel free to stop me if you have any questions or something that is not very clear, and we can have a chat about it. What I would try to do is, for the first part of the discussion, I would like to go through just an overview of what the committee that I am a part of in ARMA is. And then from there, once we have that, we can move to the topic of the discussion today. That's going to be on geomechanical support during drilling operations. Completions as well. And you can, like I said, right, the forum is open to discussion about any other aspects of geomechanical support that is required during even post-drilling operations. If the presentation doesn't cover it, we can have that in the follow-up discussion. I'm trying to give as much time after the presentation to have a bit more of an interaction. So hopefully we can address questions and have a more interactive part over there. Okay, so with that being said, I think with the ARMA part of it, I think as a community as a whole, I think my first experience with ARMA was back in grad school, where I was a part of ARMA and I started presenting at the conference in 2013 with the research that I did. For me, the presentations were more focused towards kind of a interdisciplinary part of it, because with my research, which was more focused on the thermal and mechanical coupling in lava dome emplacement, it was not in one of these conventional committees that you see, right? So first and foremost, I would say that these are kind of like the top three that you see over here. That is the hydraulic fracturing, drilling mechanics and engineering, and induced seismicity. These have kind of been the more initial concepted committees that we had at ARMA. Whereas the technical committee that we see over here for underground storage and utilization, which I am a part of, is somewhat of a newer committee that has recently been started off. And what this kind of focuses or looks at is to do more on the lines of growing interest in terms of storage, right? And that mainly comes about because of the fact that we are trying to look at different ways of harvesting energy. Not just the primary oil and gas part of it or just coal and mining and stuff, but are there other avenues from a storage standpoint where we can capture and then what you call store energy, which could then be harvested for later opportunities, or it can be done for what the industry, oil and gas, has conventionally been doing is for, say, CO2 sequestration, where it is used for EOR, not for sequestration, but for EOR standpoint. So this committee is primarily to focus on the storage part of it, and how the storage can be utilized for other sources in terms of just from an energy standpoint over here. With that being said, I just wanted to kind of also mention that one of the big, like ARMA generally has a big conference annually, right? And the conference for next year is scheduled on the 20th, from the 20th to the 23rd in Houston. I personally feel that because of the fact that it is scheduled in Houston, that would be a really good opportunity to go meet people who are in the industry. Because Houston being the hub, it would be easier, me included, I would say. It becomes easier for me to actually go to the conference. In the past, I've actually had to kind of make the statement with my team in Shell to actually be able to go to these conferences. But I think Houston would be a good one to go. So if if you guys do have the opportunity to make it to the conference for Houston, I think it would be a good one. Also, industry representation standpoint, the one committee that actually ranks quite big is the hydraulic fracturing one. And I know as a fact that you guys on the North Dakota side are much more familiar with that part of it, or will be more familiar with that part of it with all the unconventional that you all deal with, right? As opposed to me working on the Gulf of Mexico side of it. So, okay. This was basically just to give students or the people a synopsis of what the objective and the structure of the committee exactly is, right? So the committee, the underground storage committee that we have, basically is trying to do two things. One is it's trying to couple the products that we tend to store underground, okay, where it can go from, it can vary from, say, the CO2 that we basically capture and then store, the CCSU, CCUS, things like natural gas, hydrogen, nuclear has been done for quite a while. You have thermal with geothermal that we do quite a bit in different areas and stuff. And it keeps going, right? Oil and gas has its own bit as well that is done. Now, with that being said, the committee tries to couple these products where we actually are trying to store them underground with certain technical areas that are required to kind of understand things much better. And what I mean by that is, in order to store these materials underground, your subsurface requirements are kind of going to be similar. If not the same, but they're going to be similar. There's going to be overlap between them, right? And the overlap goes from things like, say, where I deal with it quite a bit in terms of well integrity, or you have, in my research, what I did with like coupled issues, right? Where you have mechanical changes taking place in your reservoir when you end up injecting, and also you have thermal effects as well that go along with it. And in some cases, I've seen a couple of my colleagues back in the lab also looked into chemical effects as well, where you were injecting and storing these materials down, right? So there's quite a bit that kind of from a technical work that has been done out for different products kind of has similarity with the products that you're now trying to store, right? So the newer products that you're trying to now store, the more recent one I would say is like hydrogen, which is gaining ground. So with that, you can actually leverage this. The committee, or the main intent of the committee, is to try and leverage already something that is being done for other products to newer things that we are trying to store, like say hydrogen, or if you're trying to do CCUS and stuff, right? Try to bring that learning into these products so that the learning curve is not that steep from there. And with the collaboration, obviously more people working on it, you would have a quicker turnaround in getting solutions. So that's kind of the main premise, or one of the big premise of our committee over here. Now, with that being said, this is basically just a more, I would say, pictorial representation of the same, right? Is you have products that you're trying to store underground, and then you have locations or things that you would do in order to kind of better understand the feasibility of storing them underground, right? So what has been done in the committee is that it's been broken up into different two different parts. One is the different themes that we have. That is in terms of things that we would want to try and understand from a how do you say, technical standpoint. That what's going on and stuff with goes on with, like, say, salt caverns where you can store these things, or you're trying to characterize things in the labs and stuff. And obviously monitoring is a big thing in terms of the what do you call it, storage and a capture and then storage of these materials downhole, right? It plays a very critical role in this part. And then obviously things with modeling and all that stuff. And then case studies help you learn from that part of it. And this basically talks about the different products that you're trying to store. So the same thing that I just highlighted over here. So these are basically the products that you're trying to store downhole or underground, subsurface. And these are the ways or things that you need to kind of look into to help you get there. So this is just lining up the technology with the kind of areas that you're looking to capitalize on. So this is just primarily the theme. And having said that, the chair for this for our committee is Richard. Richard has actually done quite a bit. I would actually personally say that his push is being quite a bit in trying to move the committee to do some of these presentations. And so today with my presentation to you guys is part owed to him as well. Is his drive to, like, okay, I guess you guys should probably take a look in this, and Taha, if you have time, good one to probably present to the students as well. So I think from that standpoint, we actually have someone motivated and good in order to push us to do stuff like that. So yeah, that part. And we do have, and part of the reason when I initially requested that we record this video is the intent would be to store and upload this video on our social platform as well. So our committee actually has a YouTube channel, and let me go to this. So we actually have a YouTube channel, and Richard actually helped set up the ARMA YouTube channel as well. So these presentations that are going to happen are going to be uploaded into the portal over here. So once you're done with this, this is going to be added to, so you see the portal for ours, right? The underground storage one over here. It will be uploaded over here. You have all the other committees as well. You have for the induced seismicity, you have hydraulic fractures as well. So everyone's trying to kind of collaborate and then subsequently upload and have information in one kind of a one-stop shop, where obviously with all this virtual learning and distant learning and all that stuff, this has kind of become like the go-to just in general. So this was kind of all I had for from an ARMA, our committee, and the setup of our committee standpoint. I don't know if you guys have a question or have any questions with regards to this before we move on to the topic of discussion for today. With that being said, let me give like a very short overview or an update in terms of what we are going to be talking about today. So I think with what Abdul Malik mentioned about the projects that I have worked on and the kind of work that I do at Shell, it focuses more on providing geomechanical support. I would say a heavy part of it is during drilling operations, but we also do quite a bit of work that's related to from a say production standpoint. So let me go to this slide. Okay. So I think from an overview standpoint, like I said, today's discussion would focus more towards operational support. And this is geomechanical support that we provide for operations while we are drilling or completing. Okay. But having said that, I just wanted to give a caveat that this basically doesn't entail the only sort of work that you would see geomechanicists actually provide in oil and gas. I think having worked for about 6 years, I think geomechanicists, from our understanding standpoint, we need to have a good grasp of quite a few things before we can start making our interpretations. That is kind of what I've actually realized after I started working. I think the biggest thing that happens is that when we are at school, we are focused, and I would say primarily from a grad school standpoint, we are focused quite a bit on the key technical issue that you are trying to solve. But I think one thing that needs to be still understood is that having a good grasp of the overarching requirements is very important. And what I mean by that is the inputs that come into your calculations, understanding where and how those inputs are calculated is key. Because in some cases, what happens is that we would fail to realize that how significant a feedback we provide in those inputs as well. And that becomes very critical. And it's kind of a key when you start working, is that it's more about the feeding back and forth rather than you just getting data from someone and saying that, okay, yeah, I have gotten the data I need. Now I can go back into my own silo or my own pod and I can get the results that I need from there. I think it is more interactive, back and forth, and especially for operations, it's key that feedback loop is constantly kept open, and it is more of a back and forth and not just data coming from someone to you. You do your calculations, give it to someone else and say that it is good. Now you do whatever you want with it. That's not, unfortunately, that's not how it works. So with that being said, today's discussion primarily will step through the drilling and completion operation, right? Now, what exactly does the drilling and completion operation basically entail, right? It starts off the inception, starts off with agreeing on a target location that you would want to drill a well in, right? Now, what I've done over here is that you see, and this is a very idealistic cartoon, right? Of a rig over here. You have a well that is drilled down and it is trying to target the oil section, right? And it's a very simple vertical well that is being drilled from top to bottom, done, right? Now, there are certain things that are what you call enablers in doing this. One is the fact that you are able to identify where you want to go in terms of your bottom hole target location. And second is that with what ease are you able to go from top to bottom? This ease in general is available for what you call onshore wells, because in onshore wells, you actually can move in most of the cases, unless and until you are restricted by residential locations and stuff like that, you actually cannot have a rig right up top of where you want to drill the bottom location, right? So you may not have a vertical well. That is when you start going inclined. So in case of what you call the Gulf of Mexico, primarily a lot of the wells that we drill are inclined wells. And that is to do because of the fact that the way it works out is we need to have some what you call infrastructure at the seafloor, okay, that limits where my ship goes. Because of that, I can only start drilling my well from this point down. So if I want to target the location that I'm at over here, I can never target that from here, right? So I would never have a vertical well to drill to bottom. I would have to actually go and drill an inclined well. So that's the first part, is finalizing what your target location is. The second is to define your trajectory that is dependent on all these constraints. Is what is my top hole location? Where do I want to go from my bottom hole location? Which are the formations that I want to target and drill through, right? So that will define my first two steps. The second, the third step, which is the one that we, from a geomechanics standpoint, come in and provide input, is in terms of estimation of the pore pressure plot. Okay, and the pore pressure plot, basically the pore pressure and fracture gradient estimates, is what we provide from the petrophysics and the geomechanics standpoint, where a lot of the inputs come in. Now over here you see a plot that is a pore pressure, a conventional pore pressure plot that is provided. The only thing that I do want to highlight is instead, I don't know how you guys are used to seeing these plots, right? Is this plot is kind of represented in equivalent mud weight, or it's represented in pounds per gallon over here, instead of doing it in PSI, right? So in PSI, what's going to happen is that these lines are going to be straight going down, right? It's going to go from, say, 0 down this way, as opposed to kind of being non-linear like this. Instead of having linear lines that go straight, you're going to have like non-linear lines in terms of equivalent mud weight. And I'll tell you why that's useful, okay? So if I don't happen to answer this question, ask me that later on in a couple of the slides if I haven't addressed that. But the key inputs that we provide, I would say from a geomechanics standpoint, is first the stresses that is the SH-min value that you see over here. And the SH-min is primarily your minimum horizontal stress, right? So you're providing the estimate for a minimum horizontal stress. You are providing an estimate for the fracture gradient that you're estimating. And the overburden is probably going to come from either you can calculate that, or it may come from the petrophysicist in the team. The way I work is I work as both. I work as the petrophysicist in the team as well as the geomechanicist. So I basically generate all these lines that you see over here. Okay. And one key input that that geomechanicists provide is the hole stability over here. Okay. That's plotted out in this dashed black line. And in a couple of the next slides, I will show what exactly hole stability is. Okay. But just to give an idea of why hole stability is important, is hole stability is critical because if you don't, if you say surface, the mud weight or the fluid that you're drilling with, it has a pressure that is lower than this dashed black line, you are going to end up having borehole breakout. Now, what borehole breakout primarily means is that you're going to have a non-uniform hole at certain points. Wherever your pressure is below your required stability mud weight, you're going to have a non-uniform hole. What that does is that it creates problems when you go in and run these casings. So you see these casings over here. When you try and run these casings down hole, they're going to get stuck. And to add to it, I literally am going through operations right now where we have an issue with that, but I'm trying to solve that. So it's not something that is non-common. It is very, it's very common, and it occurs quite frequently. What you are trying to do is do your best in order to make sure that you avoid situations like that. Because what it does is that if you have issues where your casing gets stuck, that means more money that you're spending. And that's not the intent, right, of doing a particular well. On the other hand, is if you have the fracture gradient is something that you try to adhere to, because if your fluid mud weight that you're drilling with is higher than this green line, you are going to create a fracture in your rock. So say, for instance, if just go by depth. Say, assume this is lined up with this casing string, and I'm drilling this open hole, this section over here, right? And if my pressure basically exceeds and is around at this point over here, I may create a fracture out here. And what that might do is that it will start causing fluid to lose into the formation, depending on what the formation strength is and what your shoe strength is. It may be possible that the fluid may lose down here. It may breach to surface. And you may start seeing drilling fluid being, what do you call, you have it breached to surface. That is the last thing you want to do over here. Okay, so that's why the pore pressure plot becomes a very critical piece of information, because what that does is that it feeds into how you design your casing over here, and then also it helps designing your completion type as well. Okay, so after you are done with your pore pressure plot, the other two steps in the well delivery process is you design your well, that is where you put your casings, what size casings you put, and what depth you put these casings at. Okay. And then finally is the type of completion you put in. So you can go in with a very simplistic completion, which is basically just a liner or a casing right above your target sand. This assuming that this is your target sand, right? You set up a liner or a casing right above it. You drill a hole, and you just produce through that hole. That is the most simplistic that you can do. Then you start getting a bit more what do you call technically sophisticated, where you start doing things like, say, the one that you have over here, which we do quite often in the Gulf of Mexico, is a cased hole gravel pack or a cased hole frac pack. What that primarily means is that you run you run a liner in your reservoir section over here. Then you subsequently first perforate it. So you're perforating that to get proper connection to your formation out here. And then you also run inside, you run a gravel, which is basically sized depending on what your formation is. It's basically sized to the formation so that you can ensure fluids come in, but you can still try and avoid fines being migrated from your reservoir into your either into your liner, or it ends up plugging off your screens and stuff over here. So depending on what the requirement of the formation is, you are going to be you're going to decide which kind of completion you want. Okay, so this is kind of in a gist of things that need to be done. And like I said, let me go to this slide. Yeah, and like I said, right, the pore pressure fracture gradient part of it is the one where we provide the most amount of input in the designing and execution part of a well. There are a couple of other things that we do also provide geomechanical support in. Like say, for instance, in targeting, we can look at like you would want to avoid your target that is right next to, say, a fault, right? You don't want it to be in areas where you have top seal issues. Like say, for instance, if I start producing and I end up either reactivating an existing fault, which causes my top seal breach and then communication with the shallower reservoir and stuff, I don't want that. Or from an injection standpoint, I start injecting, I basically breach, either I create a tensile fracture in the formation and then breach up, or I reactivate a fault and then propagate through the fault. Either or, I don't want that either, right? So those are things that you're trying to avoid when you're doing this part of it. And then you have certain other things that we also take into or have to take into account, things like underground venting, like I said, right, with design optimization. That is actually a big thing that we do as well, is in conjunction with the drilling engineers, you help them decide where you want to put these casings, right? So how deep do you want to go with the casing and where you want to stop in terms of drilling a particular hole section. And that is defined by these lines. So you see the black line and the dashed black line and the dashed, either the dashed purple line or the green line. These control what do you call drilling fluid weights that you can use, and subsequently how deep you can drill from previous hole section to the next hole section. Okay, so mostly I've just drawn some of these fluid weights, right? So once you say I drill from the base of this particular casing to the next casing, when I do go from this point to this point, I'm using a fluid that has a mud, or basically it has a density that matches up with this value over here. What that does is that it ensures that I don't have hole instability. That is, I have a uniform hole from the top of the hole to the bottom of the hole, so that my casing doesn't get stuck, right? And then secondly, it also ensures that this pressure doesn't exceed my fracture pressure, so that if it avoids that, I don't lose any fluid into my formation. Now, losing fluid into the formation has two very big issues. One is the fact that the synthetic based mud that is used in Gulf of Mexico is very expensive. So losing mud like that can turn out to be very expensive for the well. So you're trying to avoid that as much as possible. The second thing, or the reason why you would want to avoid that, is because once, imagine this, right, is if you start losing fluid over here, your pressure is going to reduce, because now what's happening is that the fluid is going from here into your formation. So the pressure is not exactly the same now. And if that happens, it will create a lot of issues again. And I'll show you in my next plot what that exactly means. Okay, but those are the two key things that you're trying to avoid. So that is what you're working with the drilling engineers to understand is, okay, this is the fluid weight that we can drill with. Okay, so that's why I would want to decide, or I would want to agree with my drilling engineer to start drilling from this point to this point and then stop. Okay. Yeah. Any questions on this before I before I move forward, or I ramble a little bit more?
Yes. Any question for Dr. Taha?
Yes, I have one question.
Sure.
Yeah, please.
My question is, what is the exact difference between the minimum horizontal stress and the fracture gradient? Because if the mud weight exceed the minimum horizontal stress, we will create a fracture. So what is the exact difference?
No, so the way it works out is that it depends on what you call the downhole or the in situ conditions, right? Now, if you actually have an intact rock, you should actually see something that is more like a fracture gradient value. And what I mean by that is the way it works out is if you have, say for instance, if you have a rock that is and you have stress conditions that are isotropic, right, downhole, you would see some amount of benefit through hoop stress, because when you drill a hole, that creates a stress concentration around your wellbore. That stress concentration effectively helps you go from the SH-min value over here to what is called a fracture gradient. So that is only possible when you have an intact rock. If you have a rock that already has pre-existing fractures, then you're correct. What's going to happen is that if you go drill inside, you're going to start losing at SH-min over here. Does that address your question, or does that adequately answer that?
Yes, yes. Thank you very much.
Okay. Any other questions?
Yeah.
Okay. I guess if not, you can think about it a little bit more, and we can come back. We can always come back to these slides. Okay. So this is the other part that I was talking about. So this is primarily just giving some overview of a couple of basics, right? Is things to just keep into account. Now, because of the way I'm plotting these values, there is some nuance in this, right? And the nuance is what mud weight, or I would say what density fluid pressure I'm assuming, or I get up top at surface, is going to be somewhat different from what I get at downhole conditions. And I'll just walk through what exactly it kind of means. Say for an incompressible fluid, what you're going to observe is that because there is no density variation in the fluid with pressure, the the density at the top of the hole and the bottom of the hole is going to be the same. Okay, so effectively on this plot, when I'm going to draw values, my 1 and my 2 are going to be the same. But unfortunately, when in oil and gas, the fluids that we use are compressible. So what that does is that my my density up top at the surface is different from the one at the bottom. So compressibility kind of kicks in and has an effect over here. So what effectively, when you calculate pressure, right, what it's going to do when you're calculating pressure at the downhole location, if you have a compressible fluid, you're going to have values that are first your rho g h value, assuming that this is atmospheric density, right? And then you are going to have a compressibility effect. So your downhole mud weight is not going to be just a clean calculation of this. You have to take into account compressibility over here. That's a very I would say something that you guys have must have already looked at or have seen in general. I think this the second part that I'm going to talk about is probably something that we don't deal with very often, and that is to do with the effect of circulation. So what happens is that these the two values that I'm talking about over here, the pressure 2, that is your static mud weight. This value is different from what you end up seeing when you are circulating. So if I go back one slide. So over here, I'm assuming that everything in the wellbore is static. And what I mean by that is my fluid from the top to the bottom is not being agitated at all. Like the drilling string that I have over here is steady. My fluids, I'm not moving the fluid at all. So it's kind of like think about a glass of water, right? If I'm not shaking that glass of water, the pressure at the bottom is you can effectively term it as static pressure down at the bottom of the glass, right? But the moment I start shaking it, it's going to be different, and that is because of the frictional losses that we create, or I would say frictional effect that we create, not losses, but frictional effect that we create over here, and that again adds to your value of 1 over here. So what that effectively is doing is that in general, when you're not circulating, you're going to have a lower pressure in your system. But then once you start circulating and trying to carry out the cuttings that you create in your wellbore, at that point, you're going to have a higher pressure. So it will go from 2 to 3 over here. Okay. So that is just something to take into account. Now, why does it actually make a difference? kind of to go back to the question that was just asked, right? Say, assuming that we actually had in this system, we actually had what do you call, a rock that was fractured, right? Now, if we actually had a fractured rock at the very top, you see this. If I actually had a pressure that is 3, I would have probably opened up a fracture up here, and I would start losing mud, right? But when I am at 2, I would not do that. So that is the difference. Is when my motors, or say I'm not circulating down through my my string, I have a pressure that is this, and I'm not going to be losing to the system, or I'm not going to be losing to the rock around me over here. But the moment I go to 3, I will start losing fluid, or I'll start losing drilling fluid to the formation, because I have a crack somewhere. I've opened up the crack, and then I start what do you call, permeating through the crack. So that is why you need to take into account what state you are in. Either are you in a static condition, or are you actually in circulating condition, because that can mean difference in terms of having fluid losses, or losing drilling fluid, or not losing drilling fluid. So yeah, and I guess these numbers, like I said, right, they don't, at least from top hole location to bottom hole locations, the static mud weight values don't change that much. For say depth intervals between 5,000 to 25,000 feet, in general, with the kind of fluids that we use in the drilling rigs and all, the number is about 0.1 ppg to 0.3 ppg. So it's not dramatically large, but still something to take into account from a compressibility standpoint. Yeah, any questions with this? Okay, if not, let me move for this. Okay, so I think before I get into the discussion about stresses and stress calculation and stuff, I don't know if all of you all, I feel that a good chunk of you all have kind of done these calculations in the past, right? Is in order to calculate your stresses, what you would require is an idea or an estimate of what your rock properties are. Okay. Now, the rock property calculation part of it, you can actually do by what do you call? You can do it using what do you call, theoretical equations that you have already that are available, or you can do it through empirical correlations. And empirical correlations is primarily where you have what do you call? You have collected rock samples downhole, and you're testing that in the lab, right? So you can do either or. But I think what becomes critical is for stress estimation, you would need some kind of rock property trend, which goes from the top to the bottom. And if you want to get some rock property trend from the top to the bottom, one of the easier ways that we have seen, and I know even in the industry, even in academia and stuff, is being done using velocities. Okay, so you can measure what the velocity through a given rock formation is. Okay, and then that particular velocity, and over here I'm actually just showing you a trend, right? Is basically what this is showing is with depth, what exactly is your velocity value over here, right? So your x-axis is the velocity, your y-axis is the depth, and this red line is like a velocity trend going down. And you can see similar velocity trends in different areas, right? This is one of the velocity trends in the Gulf of Mexico. You can see different velocity trends in what do you call, over in Marcellus, where like in Penn State, where I looked at it during my work, or in different, in Permian or somewhere else, right? You'll have similar trends. So this can be used in order to get an estimate of what your rock property is. Okay, you use your velocity trend, convert it into a rock property trend, and then that rock property trend will feed into your stress calculation. Okay. Okay. So with this, I'll actually not go through very detail in terms of this. This was primarily to just give people a feel of things to look out for, and we have already done, right? But like I said, one thing that we as geomechanicists provide is stress calculation, right? So over here you see the dashed purple line is your SH min value, your the dash magenta line is your SH max value, and then over here the green is your fracture gradient. Okay. Now, before I kind of move any further, right? Just to kind of add a certain nuance to this is, in general, downhole, depending on what your stress condition is, you may have a very simplistic stress condition. That is, you only you have your vertical stress. That is going to be your, in most cases, is your principal stress. That is your highest stress over here. Whereas your horizontal may or may not have an isotropy. So you may have a lower minimum horizontal stress, and you may have a maximum horizontal stress. That may not be the case every time. It may be quite evident when you are closer to things like, say, a salt body or something, or you have some tectonic effect going on. But in general, if you are in a more benign area, you may not have stress anisotropy over there. Okay. But if you do have stress anisotropy, that is going to be in your horizontal plane, then you would see a SH min, you would see an SH max, and then you can, these two are leveraged to calculate both. One is to calculate your frag gradient, depending on how you're trying to calculate your frag gradient. And then second is it's definitely used quite a bit in order to estimate your hole stability value, because the hole stability value is based on your stress input, right? What you're primarily trying to calculate is that what is your minimum stress requirement, after which you would start seeing what you call breakout. And let me go to this. And I'll talk about this slide a little bit more later, but when generally, if you start seeing breakout, right, this is what you would see as a behavior. So you see, these are the general size rock cuttings that you would get if you're drilling a normal well, okay? But if you start seeing hole stability issues, you would start seeing much larger size cuttings come out over here. And this is what you don't want, because what this does is that it effectively causes obstruction for running your casing down. That is what gets your casing stuck in generally. Either these larger size cavings, or the fact that you have a larger hole. So now your casing gets stuck at certain points that you don't want it to get stuck. Okay. So that's just for some context. So that's primarily what you're doing. And there are different ways of calculating these, the stresses and all that stuff, right? If required, I'll go into detail and stuff, but I'll try to keep it to a bit more application-based and kind of an overview of an application-based. So that's primarily what you're doing, right? Is effectively, you're trying to calculate these stresses from the rock property trends that we got, that you have derived from this particular velocity trend, right? You calculate a velocity trend. From that velocity trend, you calculate rock properties. From those rock properties, you calculate your stresses down here, okay? And then effectively, you can interpret, or you can make models that can give you a fracture gradient estimation over here, okay? So that's kind of like the sequence of moving from one to another over here. I'm just trying to go through a couple of these over here. Yeah, okay. I think I'll stop for a bit over here, check if anyone has any questions or things that they would want to kind of dig into a little bit more with either the plots or the logs that you see over here. And by the way, this is just to give people context, right? This is one of the, so what you see over here in the log is basically a sonic log that we have run. And primarily what this implies is that this is measuring your velocity, right? This is measuring the velocity downhole, and this gives you a trend with depth. So these are the kind of logs that we run, which will then go back. It'll feed into stuff like this. It'll feed into this velocity trend that you would be deriving. So I have what you call a depth-based trend, because I had run a log in my well to get that estimate. And that can be used in order to calculate stresses, and then also to do things like, say, wellbore stability and stuff.
Yeah, here I think the question is, what is the typical problem that you don't have a good calibration?
With which part are you talking about? Is it more with regards to, like, say, hole stability, or are you talking about, like, say, fracture or stresses or something?
For both.
I would say I can tell you about the consequence. and then I can tell you about how it works.
Yeah, that's the most important. Yeah.
Okay. So this is what I tell my drilling engineers when I work with them. Right. A day that is bad for the drilling engineers is a good day for a geomechanicist. What I mean by that. Now, when things go wrong for the drilling engineers, that is, if, say, for instance, while drilling, they end up getting their drilling pipe gets stuck, right? Or say, for instance, when they're trying to run their casing down, their casing gets stuck. Or when they're drilling and they start having losses in that situation. Those are days that are bad for drilling engineers. For geomechanicists, it is actually a calibration point, right? Because what that says is that your model is not exactly calibrated, right? Because the number that you gave as a dash back, the dash black line that you see over here, and if, say, for instance, the drilling engineer was adhering to this dash black line, but then if their pressure was out here and they still saw issues, that means your model was wrong, right? And I think with geomechanics, that is a key, and especially from an operational standpoint, that is a key thing to understand. Is what you need to know is your model is as good as the calibration you bring along with it. No model as a standalone is good if it doesn't have calibration, right? Because calibration proves the applicability of it. Without a calibration, I cannot tell you where my model is good or bad, right? I can give you broad ideas. I cannot give you precise answers. And that is where calibration comes in handy. So I think, yeah, so I think that is a key thing. And that is something that is very important to understand while at school. Because I know that when I did my work, and I did it on stuff like volcanic eruptions. So what I was looking at to validate my model was actually looking at surface deformation. So I was looking at surface deformation to match my my modeling numbers, and do those numbers match up? If they don't, obviously my model is wrong, and I have to go back again to the drawing board and recalibrate. So I think getting the physics right is the first key part. Setting up the model is the second key, is the next step. The third and the most crucial part is validation, right? Or calibration. Without the calibration, you've basically done, it's like this, right? You've basically made the meal, you have chewed the meal, but you've not digested the meal. The digestion can only happen when you calibrate. If you don't actually do that, you're going to throw up. That is what is going to happen. So an uncalibrated model, when given out, is basically going to cause indigestion to a lot of people, including you. So keep that in mind when you move forward. I think that is a key part of setting up things and then having them right. Okay.
Thanks.
Yeah, no problem. Any other questions?
Okay. Yeah. Are there any questions for Dr. Taha?
Okay. I guess.
Yeah.
Okay. Let me get to the next one. Okay. So, like I said, right, I think with the next parts, what we can talk about in terms of hole stability, right? And over here, I know that I kind of, there are quite a few things that I've written down over here, but the key things to take down in this case is hole stability, and either, like was mentioned, either the SH min or the fracture gradient is what drives your locations where you set your casing, okay? Because the hole stability drives the minimum mud weight requirement, whereas your SH min or your frag gradient drives the maximum pressure requirement, right? And that is the window that you want to stay in. Now, say for instance, at I just arbitrarily drew this point over here. Say at depth H, if I basically drilled my well with a mud weight of 1, okay, at this depth H, what would happen is for someone who decided to drill their well with the mud weight 1, they would get this. They would get large cavings out here, right? As opposed to someone who decided to drill their well with a mud weight that is 2, they would potentially get normal size cuttings. Now, why is that important? Is because someone who ends up getting stuff like this they're probably not going to get their casing down. They're going to have a lot of trouble getting their casing down. Whereas someone who actually gets cuttings like this, they may have a smooth ride. They will probably just, all they have to do is let their casing just like drop, and it goes down the hole and sets to the point that you want, right? And that is the result that you want, is you want to get to 2. You don't want to be in a situation that you are in 1. And that is where, again, calibration comes in, right? In some cases, calibration is only good to a point where you have 1 or 2, and you've basically been smart enough to use that and immediately get a more robust model. You don't want more, like a lot of calibration is good just from an academic standpoint. From a commercial standpoint, that is not what I want to do, right? The least number of calibrations is the best possible thing. But you're always, it's going to be a pull and push, right? Between that. You require low enough calibration that you have a robust model, but also simultaneously, you don't have a lot of commercial loss occurring. And that's how you want to balance that, what do you call it? That's kind of like a marriage. You have to balance the amount of calibration and the amount of money you lose. You can't be going heavy on one side to another. It's a negotiation. So, so in essence, that's kind of the path that you're trying to do. Is you're trying to design, or you're trying to get good calibration, but still simultaneously, subsequently, once you get calibration, you design the next well that avoids stuff like this. Okay, and there are a lot of models out there which can actually help you do that. There are theoretical ones where you can just assume perfect plasticity. There are ones which are empirical, which actually are based on the stress strain curve that you can derive from code that you have actually taken. So you can do that. So there are multiple things that you can do. There are commercial softwares that can do the same thing. But I think one key part to understand in all of them is, one, what is the theoretical background that has gone into them? And then subsequently, how well can you use that particular model to calibrate to what you see in terms of observations, right? So you can do either or. Either, say, for instance, if you're getting too many issues where you're stuck and you have what you call borehole breakout taking place and all that stuff, then in those situations, you more likely than not, you'll have to change your model. You probably are not using the best model over here. So you have to go back and take a look at the model. Or the other one is you do it the other way around, right? Is, okay, the model probably has a bust, and then people start putting like a buffer. That is not what you want to be here. If you have high calibration, the best thing is to go back and take a look at the model and see the robustness of the model over there. And the assumptions in that inherently can be changed. And there are a couple of multiple things, right? Either you change the model setup, or you change the inputs that go into it. And inputs like, say, for instance, stress direction goes into it. Your inputs with rock properties, pore pressure, and stresses go into it. You can change any of that. So there are multiple things that have to be done. But the difference is that until you don't have a calibration point, you don't know what's wrong, right? Because it's only when you get a bust is when you realize that, okay, things have to be corrected or things have to be looked at. Till then, you don't know what's right or what's wrong. Yeah, I guess that's kind of all I had on this one. Let me go to the next slide, and then I think we can stop once and we can ask if there are any other questions or more questions than this. Okay, I think this one is a little bit more heavy. Now, with the question that was previously asked, right, is how do you know that you have like your maximum pressure that you can use while drilling a whole section is going to be your fracture gradient, or it's going to be your assessment over here. Okay. One of the ways is that whenever you drill a well, once you drill a particular section, set this what do you call casing or the liner, you actually have to do a shoe integrity test or a casing integrity test. What that casing integrity test is that after you set the casing, you drill about whatever 10, 20, 30 feet of new formation that is just open hole. Okay. And that open hole, you actually pressure up. You pressure up and you see how much pressure can that particular hole take, okay, or the rock can take. And if that rock can basically take whatever, say the pressure that is mapped out till here, then you know that you're actually getting values that are more in line with your fracture gradient estimate out here, okay? But if you go in and you do a shoe test and you end up getting a value that is right around your SH min value over here, you know that probably your system is pre-fractured. You don't have an intact rock, and you are losing into pre-existing fractures over here. So in general, where you have naturally fractured systems or naturally fractured reservoirs, your highest pressure limit is your SH min, because all you're doing is reopening existing fractures. But when you are creating new tensile fractures, then you actually have initially the benefit of hoop stress. And then once you breach that hoop stress or that stress concentration, then you end up going into what you call a different zone. Because what happens is that once you break the rock, it will go from this point to this point. So your pressure effectively is going to fall. So it's going to go from whatever. If it was 10 over here, it is going to drop to 7, say, just for argument's sake. It's going to drop to 7 over here. So it's going to lose strength at that point. So this is one point in the way you know that, okay, probably this is what I have in terms of my highest pressure limit. The second way is you actually have, it's not that common, I think, in the unconventional side in terms of depletion. You don't generally see depletion, the depletion effect come into play for unconventional, but in the conventional reservoirs, we like say for instance in the Gulf of Mexico and stuff, this is a very big issue. What it does is that if you have depletion, effectively your stresses reduce, okay, and then your fracture gradient simultaneously reduces as well. So instead of having higher stresses like these where you could drill with, now you have to honor these numbers out here. And what these numbers are, I can just walk through a couple of these, right? This one, the yellow square is what is your mini frac. Now, in the conventional reservoirs, what we do is we create like small fractures that is just in order to just enough to ensure that we can move away from near wellbore damage. And once we move away from near wellbore damage, we seep into the I would say high quality rock, then we are good. And that is all that is done in conventional reservoirs. But in unconventionals, you guys do hydraulic fractures, right? And the purpose of the hydraulic fracture is different. And what I mean by different is that the scale is significantly different. And also path purpose is different. Is because you are trying to connect to, in some cases, you're trying to connect to pre-existing natural fractures to boost the flow capacity of the reservoir. In the conventional reservoirs, we are not trying to do that. Because in conventional reservoirs, more of the cases, we don't have existing fractures. So we're not trying to connect the existing fractures. All we're trying to do is we are moving away from, say, for instance, if this is my wellbore and this is my cement, I'm just trying to move slightly further out from that cement and try to produce from the actual formation or the actual rock. That's the only reason we do mini fracs. And mini fracs are in like, say, tunes of, it only exceeds to about 100 feet or something out into the formation. Doesn't go too far. But with hydraulic fracs, you can go quite a bit with it, right? So this is the primary thing. So these are the things that need to be taken into account. Is that calibrating your model? That is, do you actually have what you call values like fracture gradient that you're seeing, or are you seeing what you call a pre-fractured system where you start having issues at SH min itself? Okay, or do you have highly depleted reservoirs which may cause what you call issues while drilling, even at lower than expected pressures, right? So this is the key things that you have to look out for when you're doing that. And in the Gulf of Mexico, we actually have quite a bit of issue with these ones, and we have different implementation protocols and stuff to kind of deal with these ones. But this is kind of like the key thing. So yeah, any questions or things that you all have you would want to ask?
Yes. What about SH max? How can we calibrate it?
I would say that is the most toughest one to do. To be honest, I think even in the industry, with the tests that we do, with all the possible data and things that we have, not every field has a very good calibration of what their SH max direction is. To be honest, in some cases, they don't even know if they actually have stress anisotropy. right? You have to run very dedicated logs in order to do that. Either you're running what do you call logs that can give you an idea from acoustic logs that can actually give you an idea of stress anisotropy that is based on just the velocity difference that you measure. So we do run logs like that. Or you can interpret that from stuff like this, right? From wellbore breakout over here, like I was saying. So when you get into wells where you drill and you have, say, stability issues, the points at which you have stability issues, then you start playing around with your numbers. Let me go back to this plot over here. Like I said over here, right? When you have stability issues, say for instance, if I had stability issue at this depth H, right? And if I know that my model is good enough, right? If I think my physics to the model are robust, what I then start doing is I start playing with my SH max direction. I start playing with my SH max azimuth. SH max direction, SH max magnitude for it. And that's how I try to calibrate over here. But unfortunately, because there's so many parameters that you can, move, it becomes a more non-unique answer. So trying to calibrate stress, stress direction is, I think, one of the key uncertainties. However rudimentary it may be, I have even at work used just the which is available online is the global stress directions mapped out, right? Where you can find it on online forums and stuff. Just to give an idea of that, okay, am I kind of in ballpark agreement with what is globally observed with different areas? But that is one of the key uncertainties, which is very difficult to narrow down. Any other questions?
Yes, Mr. One question about the cementing part. Actually, can you please give us a hint, or can you explain us into a bit of more details about the importance of the mid-weight window on the cementing job? Like, we can also maybe discuss about the Macondo case or the Deepwater Horizon case, where the cementing job was done and the pore pressure was high and created these incidents. So can you just explain us a bit about the importance of the mid-weight window?
Sure, let me do this. I think doing that with a picture would be easier. Let me just draw something for you guys. I'll do new slide. And while I'm doing that, right, I think that is something that is quite critical and very important to kind of make sure that you get it right. Because like you appropriately highlighted, that is one of the key, issues, and that is one of the key barriers that you need to ensure that you have in the wellbore or in your system. So let's assume this, okay? Say for instance, if this is your wellbore, and let me draw here. Okay, so in general, yeah, okay. So basically, what I have in terms of these lines is, say for instance, for the argument's sake, this is primarily my my rock exists over here, right? So say all this is rock, is my actual formation out here at this side and at this side over here. Okay. Now this is my casing in here at this point. Okay. Now what happens is, let me just annotate this for argument's sake. Okay. So now that I've basically drilled the hole, I've run the casing to the depth that I want. Now I want to cement this patch, right, over here in this annular space between this. And what's going to happen is that we insert. See if I have an arrow just to properly. Yeah. So what's going to happen is this, right? Is over here, what we're going to do is we're going to pump cement from the top. Okay, cement is then going to turn, and it's going to start going up over here. Okay, now if, say for instance, I have what you call, say a rock formation that sits over here. Okay, say over here and at this point over here. Say if this is just let me label this as, or fill this up as, okay, yeah. So this is one reservoir, and then this is another reservoir. Okay, so this is, say for instance, this is X1, and say this is X2, right? Now, in certain cases, what you want to ensure is that if both of these have oil in them, okay, cement basically goes all the way up from here, right? So these are completely covered, and they have what do you call cement across them, so that effectively these don't kind of seep in and start leaking oil up to the surface. Now what happens is that if you don't get the fracture gradient correct over here, okay, you may end up doing something like this. Is let me draw this line. Instead of this cement going straight up, that cement will then go just here, right? So if it ends up just going over here, the issue with it only going into this section is that this section is open, right? So the oil from this section, instead of staying where it is going to start going in. Let me draw this. It's going to start going here. It's going to start going up, right? It'll breach the surface, or it'll just go through the wellbore, depending on how good what do you call your system is. It may end up stopping somewhere, or it may just breach to surface, right? Through the wellbore itself, it may just breach to surface and go up all the way through. Okay. Now, if that happens, that's the last thing that you want in your system to do. Okay. We do run different things, right? We actually run logs in order to see if one, the cement has gone in over here or not. Okay. And that can be identified by we actually have what do you call real-time monitoring at the surface location to understand whether or not the cement actually did this. Is that, did the cement go down and it actually leaked into one of the formations, or did it actually go down, turn around, and go all the way up to the point that you wanted it to go? Okay, so we monitor that real time at the surface. Sorry?
Thank you very much. Thank you.
Yeah. Yeah. So we do both. We do real time logging, and also we do real time monitoring. So if the real time monitoring shows that the cement hasn't gotten emplaced where it needs to go, then we end up doing a log. So we run a log, we see, confirm with the log, and then we basically validate that we are good to go. But yeah, this is one of the key things or key issues that we look at quite a bit. And as a petrophysicist, that is one of the key things that we are responsible for.
Yeah, thank you, Dr. Taha. So are there any other questions? I think you can continue, Dr. Taha.
Okay. I think I just have 2 more slides, so hopefully it should be quick. I think we spoke about quite a few of these topics already with regards to what could be the issues if you don't get stability correct, right? Is if you don't get the stability correct, we're not going to be able to run the casing to the depth that we want to, right? Or we would end up having to sidetrack. And what I mean by sidetrack is that, let me go back to this. So say, for instance, if I drill, if I've planned to go from this depth to this particular depth, right, over here, eventually, because I probably got stuck over here, now I can't drill a well that, or like a well that goes straight down over here. What I'll have to do is I'll have to actually now drill a well. Let me go back to this. I'll actually have to now drill a well that does something like, it basically does something like this, is it goes out from here. right? Because now I can't get to the same location that I was trying to get to. So I'll have to now drill out from this casing that I have. I'll have to drill out from this casing, go somewhere else, because this hole is gone. I can't do anything with this hole now over here. So that's one of the key things, that you don't want to be in an environment like that. So hole instability will do that for you, right? There are a lot of things that we implement in the while we drill. You have better drilling fluids. You try to optimize your trajectory so that you minimize all these effects as much as possible. And then we talk about hole cleaning. What all that hole cleaning means is that, if I go back to this, right, you try to get as many of these cuttings out from your hole as much as possible, because the more cuttings like this sit in the hole, the lower the probability of you being able to get down to the location that you want, right? So that's with hole stability. With issues with fracture gradient, the way they work out is one that we spoke about is for cementing, right? We may not get cement to where we want to. So if we don't have those numbers correct, we may not get cement where we want to. The other one is also to do with the fact that if you start having losses, it may end up leading to what's called as underground blowout. What an underground blowout is, and that is the last thing that you want in your well, is, if I go back to this, right? If I start having, say for instance, instead of this depth, if I have, let me pull this up over here, right? And this kind of goes to this depth. So I end up having, like say for instance, my fluid goes from here. It basically goes into this particular point, right? At this location over here. And I'm losing mud over here, but my effective pressure is so low that I'm actually gaining oil from here, from this X2 at this point. That is like the worst situation, because you can't control that very well. Because what's happening is that if I pour a fluid from the surface, that fluid is going to come down and it's going to go into this, because it's already losing over here, right? But what I want to close is this X2 over here. So I would never be able to close that X2 at all. Constantly, all the fluids that I'm pumping are going to fall from the top, going to go into the X1, and completely just keep bleeding into the X1. Whereas this lower section keeps pumping oil into the system. So that's the worst thing that you can be in terms of drilling a well, right? Because that is not a controllable situation. Things have slipped out of your hand at that point, right? So that is something that you try to avoid as much as possible. So when you drill wells, this is something that people tend to get scared of. So you don't want to be in that situation. And that's why you need to get your fracture gradient correct. Okay. So that's one particular part. The other goes with, we use different things. Like say, for instance, in order to avoid losses like that, or losing drilling fluid like that, you do something called, we use something called loss circulation material. Okay. It's just a fancy way of saying that you're using larger particle sizes to kind of plug up the fracture. Okay. And those larger particles can be whatever. It can be anything that is very basic, like say, for instance, as simple as walnut cuttings. We have actually put in walnut cuttings in the hole. So imagine that, right? You're putting walnut cuttings in order to block your system, to avoid one of the biggest things that you're scared of. So it can be, solutions can be as simple as that, right? But you need to know what the problem is for that, okay? So we do stuff like that, and then you do something called open hole integrity test. What an open hole integrity test is okay, so for this interval, right, like previously was asked that, okay, how do you know what is your weakest point in this entire hole section, right? Is my maximum pressure that I can go to this assessment, is it fracture gradient, or is it this number down here, depleted numbers down here, right? So what you do is you drill with a lower mud weight, okay? And then you go all the way to the bottom wherever you want, and then you pressure up, you move higher. Then you will know. So if you hit this point and you start seeing that your mud weight or your fluid is being lost, then you know that your stresses are around here, right? But if you go further out, then you know that, okay, you have something like a fracture gradient, where you have some hoop stress still over there, right? And you have losses over here, okay? Or you go to a completely higher number over here. Basically what that says is that you probably don't have any depletion in this reservoir at all. or you don't have that much of a stress reduction because of depletion, either or, whichever the case is. So that is what is an open hole open hole integrity test, and that is used an okay bit in order to understand things like these in the industry. So yeah, that's primarily all from, like, say, tackling hole stability or tackling fracture gradient part of it. Okay, that brings me to tools that you can use, right? One of the questions that was asked about stress magnitude, right? And like I mentioned, is unfortunately what you can know is probably, when I say stress magnitude, you can know your value for SH min, right? Because that is where you'll start seeing closure pressures. So your closure pressure would basically be a magnitude identification for that. But for a SH max value, it's difficult to do that. What can be done is that in these, say for instance, not open hole integrity test, but if you actually do something that is called as an extended leak-off test, an extended leak-off test where you actually have proactively created a fracture, you can probably see where that fracture is propagated from an azimuth direction, right? That will give you an idea of where your, if you do truly have stress anisotropy, and if it is, what is the preferred direction in which the stress anisotropy is, right? So stuff like that can do that for you. Or you can run, like I said, right? You can run sonic logs. Sonic logs can give you an idea of where exactly stress orientation is. You need to do some massaging of data for it, but that can give you somewhat of an idea. In instances where you have a prominent stress anisotropy, sonic logs can be helpful. But when it is much more subtle, sonic logs may not come in very handy, because then after you massage the data and all that stuff, it becomes very subjective. It's like, okay, what is your interpretation as opposed to what is truth? It becomes very subjective. We do things with, like, say, in order to identify fracture dimensions. I'm sure that in the unconventional side, you all do this much more than we do with tracers. We do it a little bit less, but when I talk about tracers, we do tracers from a standpoint of what I termed as mini frac. So when we run these mini fracs, we actually run a tracer in there, and then we map the dimensions of the fracture. But it is not done very frequently, because it's like I said, right? The time and the expense of the tool is significant. So only in circumstances where we are very uncertain do we actually run this tracer log. And then we have basic things like, say, from an imaging standpoint, where we do density images. And like I mentioned, the current well that I'm working on, that has me interpreting something like this. When I'm looking at density logs in order to interpret where we actually, or did we truly have any, what we term as borehole breakout? Did we have borehole breakout in there? And these tools help you do that. So either the density tool will give you an idea of whether or not you have a larger than designed hole, which will let you know that, okay, you had hole instability, right? Or you can also use this as an image to get the direction of where that breakout is. So that will give you the stress direction part of it as well. So those are the ways that you can identify. And then last one, I talk about managed pressure drilling. What managed pressure drilling is relatively quite simplistic. If I go back to this, my top slide over here. Yeah. So all that managed pressure drilling does is that it is an equipment that is used in order to ensure that the difference between the pressure 2 and pressure 3 is not very dramatic. Okay. It is a system that is installed while drilling, which basically minimizes this difference between the two. And in some cases, that may be the difference between drilling a well and not drilling a well, because your stress difference is so, what do you call? Let me go to this. Your stress difference is so small that a small change in pressure from the static mud weight to the density or the circulating mud weight can create losses in your system. And if it does that, then your well is gone, right? You don't have a well anymore at that point. So that system actually helps quite a bit, and it's used quite a bit, or I wouldn't say quite a bit, but it is now being used more and more in different areas. I know as a fact that it is used in Gulf of Mexico. It's also used in different, depending on the criticality of the section you're drilling, potentially can be used in other areas as well. I think this is kind of all I have from a technology standpoint. I'll go to my summary slide and then open for any other questions for the previous slides that we have. So I think, like I said, right now, I only spoke about the geomechanical support from a drilling standpoint, right? But one should be aware of the fact that there is a decent bit of geomechanical support that goes into the entire life cycle of the oil and gas industry. That is, it goes from the inception, that is from a drilling inception. And when I say inception, even in the exploration part of it, right? We come in and we provide a lot of input. Then it goes into the drilling part of it, it goes into the production, and then subsequently when you abandon the well. So literally from the start to the end, we provide information, we provide support, and we provide a better understanding of what exactly may be going on over there, right? So we do play a key role in these processes. And like previously was mentioned, right? With all these processes, with the consequences that can be so large, we actually provide one of the bigger inputs. So at work, in terms of the key process safety inputs, geomechanics and petrophysics are the ones who provide some of the big process safety inputs. So we need to be sure that we have our numbers correct, right? And that comes from calibration, like was just asked, right? That is where calibration becomes key. Because if you don't have calibration and you rely on your model more than you should rely on your model, you are in for a lot of pain when you go wrong. So you don't want to be doing that, right? And then last is understanding that uncertainty. And that uncertainty only comes in if you have a credible model. And that credible model comes in when you have a calibrated model, right? So those things should be acknowledged and kept in mind when we are building, doing our work, and then also getting it approved and checked, right? It basically is calibration gives my model more credibility. Not to say that a non-calibrated model is not credible, but the difference is that you don't know the breadth of its applicability. You can define the applicability once you get calibration. So that's all I have for the discussion. Open for any questions or previous slides or ones that we just did.
Yeah, thank you, Dr. Taha, for this these explanations and all these informations based on your experience in the field. So we are open to any questions. We have, I think, from 5 to 10 minutes for questions.
Before okay, please, Doria, the question of Doria Irofti. Could you read that question?
Yes, we have a question in the chat window, which is the reduction of fracture gradient can be handled using additives or chemical consolidation in the depleted zone. This is the question of Dunya.
Can you, the person who wrote that down, can they elaborate on the question so I can give a more specific answer? I'm not sure if I completely capture the gist of the question.
Okay, so do you want to...
While Doina, if you're there, please could you complete your question? I have a question. Here at the UND, we want to design a geothermal well. What kind of considerations we should know? Because, you know, we are going to drill a new formation, granites, drilling high temperature. What kind of consideration we should know about the geomechanic issues?
I think primarily the first thing I would go back, right, is, like I said, the gist of it is having in general, the basic thing built up. That is your pore pressure plot built up, right? I think in general, the formations and stuff that you guys are going to be drilling into, I would say with the part that you mentioned about granite and all, I don't expect a whole lot of fluids coming into your system, right? They're non-permeable, it's not going to flow on you. But what it will cause issues with is, I think, with hole stability. Hole stability is going to be one of the things that you all need to understand what it's going to do over here. The same kind of goes with the fracture gradient part of it as well. But I think in general, with the I would say the drilling windows that I've seen, or when I say drilling window, right, the gap that I've seen from stability to either assessment or even fracture gradient over on land wells is generally being relatively slightly wider to drill with. Okay. So with that being said, I think then depends on the driver. There are certain, I know from a drilling standpoint, there are certain benefits that we see in trying to drill with as low a mud weight as possible. And that is primarily, in a big way, is to do with saving money. Because what it does is that the heavier the mud weight, the more expensive it is. Because you actually have to introduce material into it to drill forward, right? So if that is the case, depending on your strategy of how you plan to drill, you would need to know one much better than the other. If you're going to drill with a lower mud weight, then you need to know your stability quite a bit. And unfortunately, if you don't, like if this is going to be your first well, it's going to be, again, right, going back to the same thing. It's going to be assumptions of what you're going to be doing over here. So in general, what we have done is we have ended up using more, if you want to get it right the first time, and it's more about proving up the capacity of drilling it, we tend to go a little bit more conservative. And what I mean by conservative is that you can probably just go with a pore pressure plot that has that assumes that you have stress isotropy and you are drilling down over there, because every time you are then exposed to the maximum differential stress effectively in there. And if that happens, then your stability, the stability requirement is much higher. And if you can still adhere to that higher stability requirement, then even if you don't have a calibration, then I guess you're fine, right? Because you're not going to hit any trouble per se. But then what happens is that when you start doing optimizations is when you need better calibration. So I think it depends on how you all plan to decide or define. But the very basic thing that has to be done is that you need to have something like this available. And in general, what we have done in areas where we don't have a lot of data is we have pulled from I don't know how close the other offset wells is, what we term as offset wells, but how close your nearest well that someone else drilled and has information for. You pull that, you learn from it as much as possible, right? Because it again comes back to the same thing. It comes back to calibration. Is if you don't have calibration, what you are projecting out is a belief. And the belief may be right or wrong. If you have calibration, you have some solid evidence to say that, okay, yeah, I'm banking on this because of the fact that I've seen X, Y, or Z from that. So I think that's the one, is you all need to, like, in terms of that development, one needs to identify the objective of how you all plan to do it, okay? And if, if there is room in terms of being able to drill from top to bottom with like higher mud weights and all, or fluid weights, then even if you don't have a lot of calibration, you may get away with it. But then as and how you'll move forward, if you'll have to do more of stuff like that, then it might be different over there.
Thank you.
Okay, I think that we have some clarifications from Doina question. So the question is, can we use loss reducing additives as well as chemical consideration of the depleted zone in order to augment the fracture gradients and avoid loss due to the reduction in fracture gradients?
We have. So depending, we have actually used in the past material in order to stop, in some cases, even improve what you call, however you put it, right? Either you put it as a fracture gradient or you put it up as, say for instance, using this as an example. We have actually done in the past situations where we have drilled the section, then put in, let's say, additives. Like I said, it may be whatever. It can be as simple as walnut cuttings and stuff, to as sophisticated in terms of additives or different things that you want to pump into it, right? And what we've done is put that into the system, started pressuring up, and when we pressure up, when, say for instance, if we if we are actually seeing existing fractures, then what we end up doing is we plug off these existing fractures over here, okay? But if we are truly seeing some intact rock, then even in the intact rock, what we have ended up doing is we have created fractures in the near wellbore region, subsequently plugged that off, and then kept increasing the near wellbore stress further up. So we have gone, not just at this point, we have actually even tried to increase it from this stress over here. So yes, we have done it in the past. In some places more frequently, in some places less frequently. Okay. Hope that addresses your question.
Okay. So are there any questions?
Hello, I have a question. Can you hear me?
Yeah, please.
Okay.
Yeah, please go.
So thank you, Mr. Taha, for your presentation. I have two questions. The first one is, could we consider the cave-in or the big size of cutting as an indicator of a kick due to the abnormal pressure, poor pressure? Sorry. And the second question is, when you have drilled the reservoir part, could we use the LCM as in the reservoir? So in the reservoir phase, like as a loss control, and also for the MPD, managed pressure drilling, because in the reservoir phase, like we try to minimize the pressure as to be near the pore pressure. That's it.
So okay, let me go through the first one, just because I have the image up here. So with the part that you're talking about in terms of looking at the say the cavings, right, in order to identify whether it is hole stability or if it is what is termed as pressure cavings, right, from one to another. We have seen it in the past. Hopefully you don't want to be in a scenario where you're seeing pressure cavings, right, because you've done something dramatically wrong. But in terms of just the shape and size of it, yes, we have seen quite a bit of it. I don't have it in over here, but in terms of our operational inventory, we do have something like that. A very basic thing, I'm sure, I don't know if you guys have already seen them, but generally the differentiator is that the instability, the hole instability kind of cavings look like this, right? They're big and they're platy like this. But the ones that are pressure cavings are more thin and splintery. They're more straight line, thin and splintery. We do have, like I was planning to put something like that over here, but I did not want to get it overcomplicated. But yeah, we have seen it in our while drilling. I've seen it in some of the wells that have been drilled by other operators. I've seen it in wells that Shell has drilled as well. Okay, so that's the first one. The second one is, I guess, with regards to the LCM that you're talking about, right? With LCM, yes, we have done it in the past. The only difference is the fact that depends on where you are trying to do, like where you're trying to execute this, right? And what I mean by this is, say for instance, if you're doing it in, say if this reservoir that I have over here is actually not is not the reservoir that I'm gonna complete my well and produce it from, right? Okay, great. So if that's the case, I think we tend to use different materials in there to pump, circulate, and then pressure up, and we are fine with it, right? But then if it is, say for instance, if this was my reservoir where I was going to complete my well and produce through, then what happens is that the amount of the type and the amount of LCM I use gets very restrictive. Because what we end up doing in that scenario is we end up using things that are more acid soluble. Because you don't want that to stay in your reservoir, right? Because then that affects your reservoir productability or producibility.
Yes. Right.
So with that being in mind, depending on your completion type, we end up what you call restricting the type of LCM that we use. We still use them, but we limit the type of LCM we use.
Great. And what about the MPD?
MPD is actually used quite a bit. In the well that I'm drilling right now, we are using that right now. So that's your answer.
In the reservoir phase?
In the reservoir phase, yes.
Okay,
it's primarily
great.
for the reservoir phase itself.
Okay, thank you.
Okay, thank you, Dr. Taha, for this presentation. And we hope that we can see you again at UND. And we end this webinar. And thank you so much. And thank you everyone for your time, and stay safe.
Thanks a lot for letting me present. And one last request is the part that I mentioned, Abdul Malik, is if you can share the video with me, I will upload the video and I'll share the link with you guys as well.
Okay, yeah, that's great. Yeah.
Thank you, Dr. Taha. Thank you, guys, UND and friends that from other countries. I think today with all from different countries and for the UND, I think that is better for us. And thank you, all of you, and thank you, Dr. Taha, Malek, and Mones, all the UND student chapter.
Thank you.
Thanks a lot. Thanks everyone for calling in. Have a good weekend.
Okay.
You.
Have a nice day and stay safe.
Please join me in thanking Dr. Taha Husain and the University of North Dakota Student Chapter of ARMA for this special presentation.